My name is TIANYU, and I'm from the University of Tokyo. So today's this is my topic, and my presentation today consists of these three parts. So first, let's start with the introduction. So we all know that with the globalization, the demand for marine transportation is increasing year by year, and engineers need to use ultra-thick steel plane to build large container ships. However, this application dramatically increased the risk of brittle fracture, which is the most dangerous form of damage. Therefore, enhancing the capability of crack arrest is absolutely needed. And actually, there are some existing studies conducted by some authority in Japan. They established a testing method for evaluating material property, arrest toughness, and developed arrest design guideline based on the experimental result of experimental result. However, the analytical aspect of brittle crack propagation have not been explored, and the generalizability remains unclear. Therefore, the phenomenon of brittle crack propagation and arrest remains fundamentally unexplored. And for the academic background, some researchers have developed a methodology, to simulate the dynamic crack propagation in 2D scenarios. So you can see that with the fine local mesh superimposed around the crack front, so and updated according to the crack propagation. So this strategy achieved high accuracy, and the node degrees of freedom decreased by 92% comparing with the conventional finite element method. And this is a visualization of the results. And next, our previous study has also proposed a strategy for simulating the crack propagation in 3D plane structure. So the entire structure is discretized with a coarse global mesh, and the fine local mesh is only superimposed around the crack front. And we used the nodal force release technique to simulate the crack propagation. And with the experimental results, so we successfully perform the calculation. These are the results. And next, I'll introduce objective and outline of our research. So as I just said, in the conventional studies, so they just the story based on the material property to trying to improve the arrestability. But our objective is to expand the target by considering the structure effects and optimizing the arrest performance by structure optimization. And the key technology for achieving this is the fracture simulators that accurately reproduce and predict the crack propagation. And actually, there are some existing studies, just showing here, but they'll have some limitations. So all our proposed strategies are based on the S method, which can address all the issues in the conventional approaches. Okay, so this is the outline of our entire research. So the first part, we already done it. It is our previous work. And the second part is my today's presentation. And third part is our future work. So we proposed this outline to address the problem I just mentioned in the social background. Okay, so let's go into the details of our proposed strategy for prediction. But before I introduce the prediction algorithm, I will introduce the modeling strategy first, so which is the prerequisite for the accurate prediction. Yes, so to represent the crack, we just simply impose the different boundary condition. So for the node located on the ligament surface, we impose the directly boundary condition. And for the node located on the crack surface, we impose the Neumann boundary condition. Yes, and here is about local mesh generation. So here currently we use the 6th order function to approximate the shape of the crack front. And using this function, we can easily locate the local node. After then, we determine the size of the local elements. So using the similar parameter, so we can easily locate the local node behind the crack front. And importantly, so for the layer in front of the crack front, we used parameter from the k+1. K+1 means the parameter used in the subsequent step. So this procedure can ensure the smooth transition when we update the local mesh. And then for the rest of node, we just simply use the distance function to locate their position. And yes, so because of the flexibility of the local mesh, so when we apply the nodal force release technique, so we can easily release all the nodes along the crack front, just like 2D cases. Yes, so this is the advantage of the S method. Then I will introduce the proposed methodology for the prediction. So first, I will introduce some what is the generation phase and application phase analysis. So generation phase is the forward analysis. So you get some experimental results, for example, crack velocity and the shape of crack front. And using this, we can obtain some for example, stress dynamic stress intense factor, stress field, some parameter like that. And all the example I showed before are just as are generation phase analysis. And application phase analysis is a reverse analysis. So it used the fracture criteria, which is the output of the generation phase analysis, to predict the crack velocity and the crack front shape transition. And yes, so because we need to verify it, so currently our target specimens are made from the transparent elastic material PMMA. So we can record, we can use a high-speed camera to record the crack propagation behavior. Yes, so these are the detailed settings of our application phase analysis. So typically we just focus on the crack velocity V and the parameter characterize the crack front shape A6 and A2. And these are detailed settings, so we just skip this part. Yes, so our optimization consists of two parts. First part is to predict the crack propagation behavior when the crack just initiated. And so because our target specimen was PMMA specimen, so here the input parameter, we assume the crack initiate from the flat shape A6, A2 equal to 0, and crack velocity start from the 300 meters per second. Then we conduct the generation phase analysis from step 0 to step 15. And here, our optimization consists of two parts. So first is the gradient descent method, which used to detect the optimal direction. And then the golden section method to determine the optimal step length. And then because the initial crack is flat, so this kind of intersection will definitely happen. So then if this case occurs, so we update A6, A2, and B, and then we repeat all the optimization algorithm again. And if it was converged, then the first part of our optimization is finished, which means we can predict the crack behavior when the crack just initiated. And then using the input parameter from the previous step, so we conduct the same procedure again, just using the gradient descent method and the golden section method. And here you can see we need to judge when the crack arrest occurred. So here we used the two very simple two judgments. First one, velocity V becomes 0, crack arrest. And second one is this kind of intersection occurred. So here, this kind of intersection occurred during the optimization. So which means the local mesh cannot be generated under this converged judgment. So which means we judged the crack is arrest. And then it's our validations. So we perform the high-speed crack arrest performance using the PMMA specimen, as I just said. And the high-speed camera can record the detailed crack propagation behavior. And these are the images captured by the high-speed camera. So we do some post-process to extract the details of crack front shape. And then, yeah, here I show in our previous study about the plane structure, we just use second-order function to approximate the shape of crack front. But for the cross-joint specimen, so currently we use the sixth order, which because it is better comparing with the second-order one. And these are the experimental results. So we can see that the arrestability is greatly improved because of the joint area. And then using yes. So as I just said, for the prediction, the fracture criterion obtained from the generation phase analysis is required as input. And our previous work already done the generation phase analysis for the plant structure, and using this relationship between the stress intensity factor and the crack velocity, yes, we used this expression as the input for the prediction. And then I will just show the results of the prediction. So we done prediction for both the plant and for the joint specimen. And you can see that these are the relationship between the clip opening displacement and crack length. So you can see the crack arrestability was greatly improved, which is aligning well with the experimental results. Yes, so finally is our conclusion and our achievements. If you are interested about our work, please refer to our papers. So thank you so much. So that's all my presentation.